Okay, so you missed lesson 4.3.4. It was honestly not a bad lesson to miss as long as you were there on the day that we finished 4.3.3 and did the mole map, because this is really just some extra practice calculating some stoichiometry problems. So let's take a look at the chem catalyst. It says if you react 6 moles of propane, then how many moles of carbon dioxide can you make? Well, check it out. For every 1 mole of propane, we actually make 3 moles of carbon dioxide. So if we have 6 moles of propane, we can make 3 times that. So even though you can do this question in your head, it's a great idea to set this up using dimensional analysis because it'll help us for longer problems later. Notice what I did here. Moles of C3H8 are above and below, like diagonally. That's how they cancel out. And then you do everything on the top multiplied together, divided by everything on the bottom, and then you write the units that are left over. So the answer here is 18 moles of CO2. What if you've got 12 moles of water? Notice how I'm always starting by writing the chemical that it gives me a number about. So 12 moles of water. For every 4 moles of H2O, you use 5 moles of O2. So I'm using the mole-to-mole ratio of what's out front of the balanced equation and making sure that my moles of water are above and below diagonally. So now I'm going to do 12 times 5 divided by 4 to get my final answer with 15 moles of oxygen. And then there's some great terminology here. Stoichiometry is all about figuring out how much of a product can you make, or how much of a reactant do you need or is left over. Then there's some practice problems. So we've got a new combustion reaction here, and it says, okay, if 1 mole of methane reacts with 2 moles of oxygen, they're getting these numbers from out front, you produce 1 mole of carbon dioxide and 2 moles of water. To get these numbers, they just added up the molar mass using the periodic table. So for example, CH4, carbon weighs 12.01, but I think they ignored the 0.01, and then each of 4 hydrogens each hydrogen weighs 1 gram per mole, so it's 12 plus 4, making that 16. So what if you only have a half a mole of carbon dioxide? Well, you're going to make 1 mole of H2O. You're going to need 1 mole of oxygen, and you're only going to need half a mole of methane. So you can see it's just literally half of each of these amounts to keep it consistent. And we'll be able to do the same thing. Half a mole of that CH4 only weighs half as much. 64 was for 2 moles, so if I've got 1 mole, it only weighs 32 grams. And they did the other 2 for us. Finally, the last set of numbers is a tenth. So they move the decimal over 1. So 0.2 moles of oxygen would require 0.1 moles of methane, and you would make 0.2 moles of the water. So now we can look at these top numbers here and just move the decimal back 1, since this is a tenth. So this would be 1.6 grams, 6.4 grams. This one is done for us, and 3.6 grams. So this table is really just helping to make sure that you're staying consistent with your mole ratios and your molar masses. So is mass conserved in experiment 1? Let's check it out. The reactants, I'm going to highlight them in yellow, 16 grams plus 64 grams is 80 grams. And the reactants, or products, I'm going to highlight in blue, 44 grams plus 36 grams also makes 80 grams. So yes, mass is conserved. How about moles? Well, yes, the moles were added up to be the same on the left as on the right, but really what's important here is that the equation is balanced, because the moles aren't always going to be conserved. It's all about how many moles of atoms there are. So I just want to make that clear. What is the ratio of CH4 to CO2? Check it out. For every 1 mole of CH4, you only make 1 mole of CO2. I'm going to highlight those in green because there's just one of those. How about the ratio of oxygen to carbon dioxide? I'm going to highlight these in pink now. 2 moles oxygen, oops, that ends up crossing it out, for every 1 mole of carbon dioxide. So this is a 2-to-1 ratio. How about if a half a mole of carbon dioxide formed, how many moles of water? Well, twice as much water forms in moles. So 0.5 times 2, you would form 1 mole of water. Why does it make sense there's not a 1-to-1 correspondence between the grams of CH4 and grams of CO2? CH4 and CO2 have different molar masses because carbon dioxide is a more massive molecule. So if you have 1 mole's worth of each of them, they're not going to weigh the same. Those oxygen atoms are larger. Part 3 is similar, it's just a different reaction. So let's go ahead and fill in the molar mass for these. We've got to add these up. 3 carbons and 8 hydrogens is about 44 grams. And 5 moles of O2. Each of these is 32 times 5 is 160 grams. 3 moles of CO2, that's 12 plus 32, 44 times 3, 132 grams. And 4 moles of H2O, that weighs about 18 grams per 1 mole. So 4 moles would weigh about 72 grams. So now it looks like in experiment 2 you used 3 times as much. So this would be 3 moles, 15 moles, and 12 moles. Now we've got to multiply these masses by 3. 44 times 3, 132 grams, 480 grams, 396 grams, and 216 grams. So what is the ratio of C3H8, there's a 1 out front, to 4? 1 C3H8 produces 4 moles of water. How about the ratio of oxygen to water? That would be a ratio of 5 to 4. For every 0.5 moles of H2O that form, how many moles of C3H8 are used? Well, let's use the equation to help us. For every 4 moles of H2O, you only need 1 mole of C3H8. Oops. 4 moles of H2O require just 1 mole of C3H8. We multiply across the top, divide by the bottom, and the answer comes out to be 0.125 moles of C3H8. So those moles of water cancel out. And then it goes through another version of the mole map, like the one that we did in class, and it goes through each step. I recommend pausing the video and reading through those to really make sense of that. It'll just take a couple minutes, so go ahead and do that now. And then let's do the your turn question. It says, what if you've got 10.5 grams of octane? How many grams of carbon dioxide would be made? Well, first step, we need to get this into moles. That will allow us to use the mole ratio between the molecules, the coefficients that are out front of the balanced equation. So we're going to end up dividing by the molar mass of C8H18 to convert it into moles. That'll be more useful for us. So that molar mass is 114 grams. Then we want to convert moles of C8H18 into moles of carbon dioxide because that's what the question is asking us about. So I got to go up and look at my balanced equation. For every 2 moles of octane, you actually make 16 moles of carbon dioxide. And then we're not done. If we cancel out all the units, we can see that we're still in moles of CO2. We want to get this into grams because that's what the problem asked. So we got to go to the periodic table and add up 1 carbon and 2 oxygens, and it adds to about 44 grams. So then I multiply everything on the top, 10.5 times 1 times 16 times 44, divided by, be careful here, use parentheses in your calculator, 114 times 2 times 1, parentheses. My final answer is 32.4 grams of CO2. Okay, let's take a look at the check-in question. Another stoichiometry example. Okay, what if you want to produce 190 grams of Na2O? We want to figure out how many grams of that sodium are we going to need to do that. So again, first step is get grams into moles so that we can use the mole-to-mole ratio in the balanced equation. So I've got to add up from the periodic table 2 sodiums and 1 oxygen. That adds to 62 grams. Then I've got moles of Na2O, and I want to get this into moles of Na. So I've got to use the balanced equation and the numbers out front. Oops. For every 4 moles of Na, or every 2 moles of Na2O, I should say, you make 4 moles, or you require 4 moles of Na. Said that really badly, sorry. Now, last step, the problem asked for grams. So 1 mole of sodium is, on the periodic table, 23 grams. So now I'm going to multiply everything across the top and divide by everything on the bottom, which brings me to my final answer of 141 grams of sodium. And then let's take a quick look at the homework, the last piece here. We've got a different balanced equation, and it starts off, it says, what if you've got 6 moles of sulfur? How many moles of copper do you need? Well, for every 1 mole of sulfur, you need 2 moles of copper. So you're going to multiply 12 moles of copper. What about the mole-to-mole ratio of Cu to Cu2S? It's 2 to 1, the numbers out front. Sulfur's got a 1 in front of it, and so does Cu2S, and then 1 to 1 also, just said in the opposite way. So one more question. What if you produce 10 moles of Cu2S? How many grams of copper did you use? Okay, well first let's get moles of Cu2S into moles of copper. The ratio is 1 to 2. So now that we've got it into moles of copper, we can convert it into grams. 63.55 grams is how much 1 mole of copper weighs. So we're converting moles of Cu2S into moles of copper, and then converting moles of copper into grams. So this would end up being 127.1 grams of copper. Now, before we do this last question, I recommend pausing and trying these on your own first, even if you're struggling. So it first asks you to list out all of the ratios. So every 2 C4H10 produces 8 CO2s. You could also write that as a 1:4 ratio, same thing. For every 2 C4H10s, you produce 10 H2Os. You could also write that as a 1:5 ratio. For every 13 O2s, you make 8 CO2s. And for every 13 O2s, you make 10 H2Os. So those are all of the ratios of the reactants to the products. We could also do reactants to reactants and products to products, but that's not what this asked. So first one is going to be a short one. You've got 5 moles of butane used up. How many moles of water did you produce? Now, this should say, assuming that you had an excess of oxygen gas, because of course you need oxygen to even start the reaction. But we're going to get moles of C4H10 into moles of H2O. For every 2 moles of C4H10, you make 10 moles of H2O. Multiply across the top, divide by the bottom, and you get 25 moles of H2O. Last question, what if you use 10 moles of oxygen? Then how many grams of carbon dioxide are produced? Again, they should really say assuming you have an excess of the C4H10, but we'll forgive them. So first we've got to convert moles of oxygen into moles of CO2. So let's use our ratio that we already figured out up here. We've got O2 to CO2. 13 moles of oxygen produces 8 moles of CO2. And it asks for grams, so our last step is going to be to convert moles of CO2 into grams of CO2. And sometimes you'll see molar masses get a little bit off like this, where it uses like a slightly different decimal. That's why you're showing your work, because in the end it won't really matter. Multiply everything across the top and divide by the bottom, and you get 271 grams of CO2.